Then the next one, right, that we want to look at is GoogleNet. That is again, I mean, in terms of number of layers, it's only significant. I mean, it's not very high. I mean, it's a small jump from 90 to actually 22. And even in terms of the accuracy, right, it's like a small improvement, right, 7.3 to 6.7. But this improvement is also, we can't ignore it, because as I said, right, as you go downwards, right, it's going to be harder and harder. But there are certain things, right, that a GoogleNet brought in, which have been then used across the board. Okay, certain ideas that they brought in, which of course helped the image sort of classification challenge, but there is something else, right, which also it triggered, okay, in terms of understanding what is called an Inception module. Okay, and this Inception module is now kind of widely in use. Okay, what their argument, right, everything, so their argument hinged on actually something called a 1 cross 1, a convolution. I mean, see, for example, if in a DSP course or in a signals and systems course, if I told you that I have a 1 cross 1 filter, right, what would you think, right, it can do? If I kind of pass an input and I have an impulse response which is 1 cross 1, what will happen to the input? It will just scale it, right? I mean, all that can happen is either if you don't have any, you just have 1 there, then the input will just come at the output. If you have some number there, a times, it will just become a times, right? Can a be a complex number? Yeah, right. It can be a complex number also, right? So whatever it is, right? Whatever a times delta t, and then right xt goes in, yt is simply a times xt. That's what will happen. But this 1 cross 1 convolution is not that. Okay, it's also like a single sort of a pixel alone, but then thing is, right, it is acting along the say feature maps. So what is called a depth slice, okay, that's another sort of a terminology to use. I mean, I keep using feature maps, but some people will say depth slices. Okay, so you have the number of feature maps. If you say that I have a depth slice which is higher, that means I've got deeper, I've got more number of feature maps. Okay, so this 1 cross 1, a convolution acts along the depth. And the idea is that, right, any time, I mean, right, not just for this example, okay, but the idea is very significant, because this 1 cross 1, a convolution, you can use any time you want to actually bring down something like a big volume that you have with you. If you want to convert that into a 2D feature map, right, you can always do it. I mean, you can just use this 1 cross 1, a convolution, and then aggregate all the information, right, bring it down to a 2D feature map. If you want a 3D feature map to come out, that's also possible. You just have to use multiple box filters. But the idea was that, you could, the first thing is that using a convolution, a 1 cross 1 convolution, which I think, till then probably nobody even thought about a 1 cross 1 convolution, right, because generally we don't talk about it. But here the idea is that the filter will have different values for each feature map, right, as it acts along the depth. And so right, that way you still have a filter, a box filter, which you can then translate all over. What will happen when I have a whole volume there, and then I'm kind of, right, sending this box filter all around, it will give me one 2D feature map. So they said that, right, this way you can aggregate all the information, bring down the number of unknowns that you have, or for example, otherwise, you would have to, not just the unknowns, what I'm saying is the number of feature maps, right, which you have to actually deal with, you can aggregate all that information. Now, whether you lose out, right, in the process, whether you gain and all, right, I mean, it depends upon where you actually put it and then how you use it and so on. But the way, right, in this thing, okay, in this, GoogleNet, the way, right, it was run, by the way, this was by Zegidi 2014. So as you can see, right, these are not all that old and all. I mean, by our time scales, right, these are all pretty new that way. But then so much has happened. I mean, the funny, the sort of strange thing is that, even though 2014 looks like just about 7 years, 8 years ago, but so much has happened, right, in the last, especially in this area, right, every day tons and tons of these papers get uploaded and archived, and everybody is trying out something. Therefore, the rate at which things change is very, very fast. Okay, so 2014 is now old, by the way. Okay, so the key idea was this, right, efficient, right, Inception module. And if you see, so the Inception module had actually, right, two things. I mean, I'm not writing these things, but maybe some points, right, I'll still write, just for the sake of. So if you think about GoogleNet, okay, some of the main things, right, I'll just write down. Okay, why? So the key ideas, one of the key ideas was this Inception module. I'll write and then I'll actually explain, okay, what this should do. Want me to write bigger, or this is okay? Okay, so, right, so the idea is what, use multiple filter sizes in parallel. See, multiple filter sizes, right, we have already seen. Like for example, you could have had 3 cross 11 cross 11, then we use something else, right, 5 cross 5 somewhere along the line, but then in parallel, right, whatever we did till now was all like sequential. One layer will do a 11 cross 11 convolution, then the layer following that may do a 5 cross 5, then the layer following that may do a 3 cross 3, but then in parallel, right, we did not see it till now. Like for example, you have all these filters coming together, right. So in parallel is very important, multiple filter sizes, okay, multiple filter sizes coming together in parallel. And then there was a concatenation idea, right, which was again sort of new. See, concatenation in terms of combining that is multimodal inputs was kind of known, but then concatenation of feature maps and all, right, which was still sort of a novel idea. So this, right, so this is like act together, okay. So this was, they all had to act, right, simultaneously. So multiple filter sizes. So what they introduced was 1 cross 1, 3 cross 3, 5 cross 5, and then in fact they even had a max pool block. So they had all these guys together. I mean, but normally, right, you would have seen them acting sequentially. Max pool coming after some time, after a convolution block and so on. But in an Inception module, you see that they are all kind of coming together in parallel. Okay, and this 1 cross 1 is also called a bottleneck layer. Okay, bottleneck layer, because because it actually reduces the dimension of the feature map. I mean, not spatially, but then depth wise. So it's like having a highway, right? That's that wide, and then you suddenly shrink it to a single feature map, right? That's a bottleneck, no? I mean, otherwise you would have had so many of these channels, right? And you're suddenly, right, bringing them all together, constricting them to a narrow sort of a lane, right? So it reduces the dimension of the feature map. So this bottleneck layer is often used when you talk about autoencoders and so on. But even this 1 cross 1, right? People, it's not unusual to refer to them as bottleneck layers. Okay, now let's just go back to that figure, right, and see, okay, what it is. So here we were. Okay, so if you see, right, what they have is a previous layer output, okay, which is whatever was earlier. Of course, and you also see something here. I mean, so the Inception modules are all sitting here, right? As you can see, this is one Inception. They've got several of them. Okay, so they've got several Inception modules, and then right now, right, let's not worry about this and this. Let's just kind of look at the Inception module. Okay, so if you look at the Inception module, right, it's kind of taking the output from a previous layer. That means, right, so for example, this guy gets input from a previous layer, and that layer, okay, and then what happens is you actually right, use a 1 cross 1, this one, a convolution. But then what you do is, it's not like, right, you completely reduce it to actually a 2D layer. So what they do is they use multiple box filters, again 1 cross 1 convolution, but then they reduce the number of feature maps. Typically it will be like half the number, okay, that you might have had here. So for example, if you had 512 feature maps, then very likely that you have, I would say, right, or 256 feature maps here. That means you got like 256 box filters. One box filter will give you one feature map. 2D feature map, you have like 256 of them. I'm just giving as an example. So you have much fewer numbers here as compared to what you have here in terms of the number of feature maps. And similarly, right, you have something here, 1 cross 1 convolution, and then this right, you have some kind of a max pooling. Okay, so max pooling is also a part of the right, Inception module. Okay, and then after this, right, what they do is then you have a convolution filters of kind of various types. So you have a 1 cross 1 convolution which is coming straight away from here. So this layer in the Inception module, it has actually two things, right, a bottom layer and then a top layer. In the bottom layer, right, I mean, you have two 1 cross 1 convolution coming from here, and again these filters are not identical. Okay, the box filters that are doing the job here are not identical to the box filters that are doing something here. Okay, so these have to be learned separately. Max pooling, no unknowns to be learned there. And the second layer is all simply a convolution, but then like I said, multiple filter sizes. So you got like 1 cross 1, you got 3 cross 3, 5 cross 5, and then 1 cross 1. Okay, and again, right, I mean, the right, number of feature maps and all they have. I mean, if you see the architecture, it will tell you how many feature maps is there out here. But then in terms of the overall numbers, okay, if you were to do a naive job, see for example, right, I mean if I try to use a previous layer from here and then right, if I skipped this guy and suppose I directly operated here, right, then the number of feature maps, right, that this would have to operate on will be much higher, because whatever is here, right, this 3x3 convolution has to act on all of them. So this in between layer is actually bringing down this depth, okay, significantly, so that these filters, when they act, then they act on a smaller depth, okay. And then this sort of a concatenation idea, of course, to concatenate, one of the requirements is that they should all be of the same size. I mean, you can't concatenate different sizes, okay. So concatenation means that you just put them, stack them all together. So what you will do is whatever output comes from here, so it will be a set of feature maps, then you actually again you have to zero pad and all properly. That's where right, till now we didn't use zero pad that effectively, right. It just looked like, okay, if you wanted to do something, just use a zero padding. But here is where if you wanted to concatenate feature maps, you can use actually zero padding is one sort of tool that is available to you, wherein you can actually adjust the padding such that what comes out of one box, that same dimension you can actually maintain across the block. So you would have to use appropriately again here, and then right, and then okay, this is a 1 cross 1 convolution, and you will get again feature maps corresponding to each, coming out of each of those blocks, and then you stack them all together. Okay, that is a concatenation, and that concatenated output is what then goes as input to the right, next layer and so on. So the key thing, okay, two kind of key things. One is multiple filters acting in parallel, multiple filter sizes acting in parallel, which you didn't see till now. Second idea is this 1 cross 1, this one, a convolution, right, which again was something that right, we did not see before. And it turns out that having an architecture like this, even though this is not very obvious, for example, if you and I were to sit down and think about, okay, what might be a good improvement, it's not very obvious that we would have struck upon this idea. See, it's also something, right, it's not like very obvious that, right, one would have thought about an architecture like this, but then the fact is, their group worked on it and then they came up with this architecture. And this one, right, this is called an auxiliary. Okay, there is one thing, okay, which of course I couldn't talk about for lack of time. I think there is something that I just mentioned along the way. There is a vanishing gradient problem. Okay, in a deep network, okay, there is something called a vanishing gradient problem. There is also an exploding a gradient problem, but typically a vanishing gradient is what is most common. So what this means is that, right, by the time you actually propagate the gradient information back to the input, right, because right, from all the way from the loss at the output, I mean you have to come all the way to the input. Now you are hoping that your gradient will still be significant, right. That is when the weight update will happen, right. If you go back to that GD, okay, that it's like theta n plus 1 is equal to theta n minus some alpha times dou L by right, I mean dou this one theta, evaluated at theta equal to theta n. Now that there is a gradient dou L by dou theta, which you can of course write in terms of all the right, involving the right, I mean all the slopes, right, in between. So when you come all the way from the output to the input, right, this number, okay, you can show that sometimes if you go deeper and deeper, right, this gradient can become very, very small. Therefore, even though you are having a gradient which is not 0, but then the gradient becomes so small that it almost vanishes. Therefore, when you try to apply an update, right, the update either can become very slow or it's almost not there. It's going to say negligible, which means that you are stuck, right. I mean you can't even move. And therefore, right, people, so in this network, right, what they have done is they have added an auxiliary network which has some very, very simple blocks. But this auxiliary network, right, has so right in between, I mean it's not everywhere. If you notice, it's not in every Inception module. It's been thrown in, right, I mean here and there, right. So it's thrown in here, it's thrown in here, and the idea is that, right, so the idea is that the final classification loss, right, is also recomputed, okay, at these places. Okay, we don't want to spend right not too much time, okay, on Hawaii and how it works, but then the general idea is to handle the vanishing gradient problem. You also have an alternative way by which the gradients do not simply, right, go down to 0. So this auxiliary network is mainly for that. I mean, it just wants to make sure that, because because you have so many layers, right? How many? This is about say 22, right? So until now, among the deep networks that we have seen, 22 is still the highest. The next one that we are going to see is far higher. That's like 152 layers or something. And there, of course, this vanishing gradient problem will look like an obvious thing that will happen. But even with right, 22 layers, okay, it could still be a problem. But, and therefore, this auxiliary network, right? I'll just write a few sentences about it, and so that, right, I mean, for those of you who are more interested, you can go and read it up. So this auxiliary network, this is all for GoogleNet, okay, by the way. So the auxiliary network, okay, so this is mainly needed to improve the strength of the gradient, needed to improve the strength of the gradient, gradients, which means that it has a classification loss, by the way, okay, that is why it is able to improve the strength of the gradients. Then okay, concatenation is okay. So zero padding, I think, and I've already said. Then the other one is a stem network. I mean, that's like a preprocessor. Okay, see, this one looks like a stem, right? I mean, in the bottom, okay, what you saw here looks like a stem, right? So this one, right? This looks like a stem. Okay, so it's called literally a stem, network, and that's also, I mean, that's nothing very significant. Let me see, right? If I can blow up and show you what it has. I think it just has a conv layer, a max pool, and then a batch norm or something like that. Very simple stuff. Okay, so the stem network, that is okay. This is a pre-processing module before the first inception module. Okay, this is like a preprocessor before the inception module, before the first inception module. Okay, not everywhere. Okay, before the first inception module. And yeah, we can see, I mean, right, what it has. And there is one more thing, right, which these people introduced. I mean, we have seen max pool and all, right. Now, what they also introduced was, so what happens is, okay, towards the final stages, right, you do what is called global average pooling, or what is called gap. See, it's hard to right, keep in mind all the feature map sizes and all, but just what matters is this idea, global average pooling. So what this actually, right, does is, I mean, towards the end, right, you can actually check this, okay, with respect to GoogleNet. So when you are done with the last convolution layer, at the last convolution layer, okay, that's not coming out in that figure. Okay, when I blow it up, I don't think you can see that. In the last convolution layer, you have feature maps which are of size 7 cross 7 cross, or say 1024. Okay, that's the size you have. That means you've got 7 cross 7 spatial dimensions, and you've got 1024 such feature maps. Okay, now if you try to unroll this, right, and try to then put in a fully connected layer after that, right, that will simply blow up, correct? Because you've got, like, here itself we got 7 cross 7 cross 1024. So what they do is, unlike the max pooling and all which we saw, there's also something called average pooling, right, that I mentioned. You can have 3 cross 3 average pooling and so on. So instead of that, they do what is called a gap. Okay, this is called GAP. Okay, gap. So this global average pooling, what it does is it takes the complete average, right. So here you have a 7 cross 7 filter. It just boils it down to one value. Just takes the complete average of that feature map. Right. So it's called a global average, right? No longer like local average pooling or max pooling that is locally happening, right? So they just take the average. I mean, you can ask them, could they have done a max pool on the entire 7 cross 7? Maybe, right? But then what they advocated was this. Okay, again, right? In all of this, there are so many things in which one can do. Okay, just that we are only trying to tell what they have done. Okay, so what they did was, so they just reduce it to one number. Okay, reduce it to one value. Okay, through gap. Okay, and that way, right? That way, this whole thing could have say reduces to 1024 dimension instead of 49,000. Now it is just 1024. and this 1024 then kind of goes into the FC layer. That is why if you look at the parameters, right, this this guy has far fewer. Okay, so if you look at the number of parameters, let me see where I've got the parameters for GoogleNet. I think it's about 5 million or something, if I'm not mistaken. Let's see in the figure, somewhere it should be there. Yeah, only 5 million. So you can see, right. So what has happened is, towards the final thing, once they did this global average pooling, right, so just shrunk down to 1K, and after that, they had a few FC layer, fully connected layers, but all of that put together still is far lower than so it is actually 12x less than AlexNet. So you should see the power there, right. I mean, there you had 60 million and you're getting 6.7% top five error with just 1/12 of what you had used for AlexNet, right. So that's also the reason why this network is actually a powerful one, because again, it's hard to kind of pin it down and say, which one is, which one probably was, how to account for each one of those, how to account for this improvement, right, through each one of these modules is hard to say, but you can definitely, but overall, right, the sense is that getting this insertion module is actually a key. And then this global average sort of a pooling where maybe people were afraid to do, right, prior to that. They thought if you did something like that, then maybe you would lose out information. For example, at such averages and all, when you do a regression problem, typically you don't do such kind of things, because what you need are finer details, and any averaging, right, will make you lose information. So not usually, right, so you won't kind of think along those lines, but these people went ahead and so at the end they kind of did that, and then they showed that with just 5 million this one parameters, right, they could do so well. Okay, then is there anything? So Inception model, I think I already told you, 1x1 convolution I told you, concatenation I told you, right. I think all this is there in the slide. I think it's easy for you to understand. Okay, and I think the so for example, so if that in between layer was not there, right, Inception model had one thing here, right, 1x1 and a max pool. Without that, right, I mean, there is also this, what if you had a naive Inception model without that, then what would happen? So I think, right, these are all things, okay, which are now easy to understand for you, and you can actually find out, okay, and what you gain and what you lose. So all that is here. Okay, now let me go to, okay, so this is a naive model, which if you use, right, you will actually run into trouble. So this is the one that they use, which leads to a dimensionality reduction. Then bottleneck layer, I think I told you. Yeah, I think I thought it's easy to explain first, and then the stem network, right, I told you. What else is there? Auxiliary classification to actually inject a gradient at lower layers. I think most of it is here.